Hi guys, welcome to my new video. We're going to be doing some real world maths today, so a little bit exciting. And I want to preface the video by saying I do not want to get involved in any culture war. This is purely to do with the maths. You'll see what I mean in a sec. So the other day I was in the car driving to work and I nearly hit a cyclist. In the end everyone was fine. I'm going to show you the footage in a sec. But he did ask me how fast I was going, and I didn't know. I wasn't checking the speedo at the time. I think I was okay, but we're going to use the footage today to try and figure it out. So first of all, here's the footage. It's not very exciting, don't worry, I've bigged it up. It's pretty boring. Right, yeah, so not very exciting stuff. He sort of stumbled, that was about it. But anyway, he asked how fast I was going, so we're going to use two methods to figure out the speed I was going at. The first one is similar to the one the speed cameras use. You might have seen on the road, you have those little sets of lines, and then you have the camera here. Fantastic. What it does, it takes two photos, one when the car is here and one when the car is wherever, and it calculates the distance between them. And it knows the time between the photos, so it uses the old, you might remember this, speed, distance, time pyramid thing. So if you want to work out the speed, which is what we want, you do distance divided by time, okay, d over d. If you wanted to work out the time, it's d over s, and if you want to work out the distance, it's s times t, speed times time. Okay. So we know that. So what we've got in the video, if you remember, was some lines on the road. So what I'm going to go and do now is measure the lines on the road, and then we'll be able to take 2 points, say here and here, measure the time between them, and we'll be able to work out the speed using that. So I'm going to go and do that now. Right guys, I'm here to measure the white lines and the gap in between the line. I've come in the middle of the night because there's no cars, so, but I still got them quick. So the white line is 3.2 meters. The gap is 1.9 meters. Right, let's go back inside because it's freezing cold. Right, so the lines were white line, what did I say, 3.2 meters, and the gap in between them was 1.9 meters. Now I've looked at the footage again, and I've sort of started the video at the start of one of these white lines, let it run for until I've reached here. Okay, so this is the start, this is the end, and I've timed it. It took 38 frames in the video. Okay, 38 frames. My videos run at 30 frames a second, so that means that's 38 over 30 seconds. So that's the time it took, and then we need the distance. So that's 3 times 3.2 plus 2 times 1.9 is equal to 13.4 meters. So now we do, as we said, don't forget this, distance divided by time, 13.4 divided by 38 over 30, and that gives us, bear with me, 10.6 give or take meters per second. So what's that in English, right? Well, what we need to do is find out how far that is in an hour. So there's 60 seconds in a minute and 60 minutes in an hour. So we do 10.6 times 60 times 60. That'll give us in meters, and then we divide that by 1,000 to give us in kilometers. So this will be kilometers per hour. So that's equal to 38 kilometers an hour. We live in England, you still use miles. So what's that in miles? Well, we'll use the 5/8 rule. it's not 100% accurate, but it's like less than 1% out. So we use that times 5/8 gives us 23.8 miles an hour. Miles per hour. Now luckily I was in a 30, so I was well within the limit. So phew. All right, so we're lucky because we had the markings in the road, but if we didn't have those markings, could we have still figured out how fast I was going? Spoiler alert, yes we could. What I'm going to use is, if you remember in the footage, there's a lamppost that I'm heading towards. This is at the end of the road. Here's the car here. Vroom, vroom. Heading towards this lamppost. Now I've taken a few measurements. Now at one point it was 4 centimeters big on my laptop screen. So at this point it was 4 centimeters big. At a later point it was 6 centimeters big, and then at a point after that it was 8 centimeters big. I chose those points on purpose because they are in a 2:3:4 ratio. Okay, so we're going to call this angle 2 alpha, say 3 alpha and 4 alpha, because they're in this ratio. We've got the height of the lamppost here. We don't know that yet. We don't know what the angles are either, because we only have a proxy for the angles, that is the size of the lamppost on my screen. And I know the times here. This time from here to here took 57 frames. This time from here to here took 27 frames. Now you can have a go at measuring some of these yourself. Go back to the footage and stop and start it if you want to double check these figures. So we're going to use this info to try and figure out how fast I was going. We're going to call this distance x1, this distance x2, and this distance, surprise surprise, x3. And we're going to get some equations linking alpha, x1, x2, x3 and h, and we're going to solve them to figure out these distances. Then I have the times and we'll be able to figure it out. So if you remember your trigonometry, if we look at the big triangle, this is 2 alpha, worst alpha ever. This is h, and so we have, and this is the sum of all three. So we have here h over x1 plus x2 plus x3 is equal to tan is opposite over adjacent. So tan 2 alpha. The second triangle will give us, that's 3 alpha, and that's just the two of them. So we have h over x2 plus x3 equals tan 3 alpha, and similarly h over x3 equals tan 4 alpha. We also have one more equation. We'll call this equation 1, 2, 3, and then we know, if we assume I'm going at constant speed, then we know that this distance x1 divided by the time it took is equal to this distance x2 divided by the time that took. Is that right? 53 frames. This was, I gave you the wrong figure. 53. Okay, and that's equation 4. So now we've got 4 equations, we need to solve them. It's a bit of a mission, but bear with me, we'll go through it. Okay, first of all we have to put these in terms of tan alpha. So if you remember our compound angle formulas, tan of A plus B is equal to tan A plus tan B over, or minus tan A tan B. Okay, and we can use that in all of these examples to get, for example, tan 2 alpha equals 2 tan alpha over 1 minus tan squared alpha. Similarly, you can get tan 3 alpha is equal to 3 tan alpha. Hang on, let me hold it up here. Minus tan cubed alpha over 1 minus 3 tan squared alpha, and then tan 4 alpha is equal to 4 tan alpha minus 4 tan cubed alpha over 1 minus 6 tan squared alpha plus tan to the 4 alpha. Okay, so it gets pretty complicated. Rather than keep writing tan alpha out all the time, I'm going to set equal beta equals tan alpha, just so it's going to be a bit easier. And now I can rewrite all of these equations in terms of tan alphas, i.e. betas, which I will do now up here. We have equation 1 is now, and also I'm going to split these up in a minute, so I'm going to take the reciprocal of both sides as well. So we're going to have x1 plus x2 plus x3 over h is equal to 1 over tan 2 alpha, so that is equal to 1 minus beta squared over 2 beta. That's using our beta equals tan alpha substitution. That's the second equation. Then becomes x2 plus x3 over h is equal to 1 minus 3 beta squared over 3 beta minus beta cubed. Equation 3 becomes x3 over h equals 1 minus 6 beta squared plus beta to the 4 over 4 beta minus 4 beta cubed. And equation 4 remains the same. x1 equals, let's just multiply up, shall we, 53 over 27 x2. Okay, so there are 4 equations. Now we've got to solve them. Get rid of this. So what I'm going to do is I'm going to put this into here. This will give us x2 over h equals, plus this, because this is x3 over h, so I'm putting this expression in here, equals this, and then using 3 and 4 into 1 gives us, because x1 is equal to 53 over 27 x2 plus x2, that's over h, plus again this x3, 1 minus 6 beta squared plus beta to the 4 over 4 beta minus 4 beta cubed is equal to, from this equation, 1 minus beta squared over 2 beta. Well, this is equal to, this is 27 over 27. So that's 80 over 27 x2 over h equals, and then minus this thing, rearrange this equation to give us x2 over h equals 1 minus 3 beta squared over 3 beta minus beta cubed minus 1 minus 6 beta squared plus beta to the 4 over 4 beta minus 4 beta cubed. Put that into here, gives us 80 over 27 1 minus 3 beta squared over 3 beta minus beta cubed minus 1 minus 6 beta squared. Equals So it looks a bit crazy. It is a bit crazy. You can stick that into Wolfram Alpha now and that'll give you the result, or you can do a lot of cancelling down. It's complicated and it's not very fun because it's tedious, but you eventually get down to something a bit simpler, which is, if I can see it, equivalent to 2 minus 210 beta squared minus 426 beta to the 4 minus 214 beta to the 6 equals 0. This is a cubic in beta squared and it does factorise, believe it or not. So yeah, it does factorise. We get minus 2 lots of beta squared plus 1 squared times 107 beta squared minus 1. So this has got a couple of real roots and a few complex roots. We don't have to worry about them, and we're going to have a negative root here. We can ignore that as well. We only want the positive root. So we set this equal to 0, minus 1 equals 0. That implies beta squared equals 1 over 107, and beta equals the square root of 1 over 107. Now going back, we remember that tan alpha is equal to beta, so we actually now have, we're getting there, guys. Take the inverse tan, gives us alpha equals, give or take, 5.5 degrees. Okay, so there we go. So we've got an angle. Now we need, remember our original triangles have angles in terms of alpha, and then this, and we want to measure some of these distances here. Okay, so now we need h. So what I did was I didn't climb the lamppost and measure the height because a bit crazy. Instead I waited for a sunny day, which was last Friday, was it? And used a little trick which I'm going to explain to you now. It wasn't very exciting. There's a picture of me with the shadow, and here's a picture of me measuring a stick that I'd put in the ground. Okay, so we have the light coming in from this angle. Here's the lamppost with height h, and this is the shadow, length L. Okay, so I measured length L, and then I put a stick in the ground of known height. I measured it, and I measured its shadow. Okay, and the ratio of this to this is going to be the same as the ratio of this to this, because they're the same shape, because they've got the same angles. These are 90 degrees, same angle, because the sun's light is parallel. So the measurements I got were, this was 1.1 meters high, and this is 3.4 meters long. Okay, and h I don't know, that's what we want, and the shadow was 32.7 meters. So what we know then is h divided by 32.7 is equal to 1.1 divided by 3.4. Okay, the ratios are the same. All we do is multiply up by 32.7 to give us h was equal to 10.579 meters. There's going to be some error there. Let's say 10.6, right? So our original thing, we got 10.6. We got 2 alpha, which is 10.11 degrees. We got another one here, which is 16.5 degrees. Okay, we got, this takes 53 frames. That is 53 over 30 seconds. We know this distance is 10.6. Sorry, we know 10.6 divided by this distance, let's call it x now, is equal to tan of 16.5. To solve for that, we go multiply it by x and divide by tan 16.5. We get x equals 10.6 divided by tan 16.5. So this distance is now equal to, I need my calculator, 35.7, where's my pen? Alright, 35.8, sorry. And then this distance in total is going to be equal to 10.6 divided by tan of 11. and that's equal to 54.5. 54.5 minus 35.8 equals 18.7, and then that's the distance. We divide it by the time to give us 10.6 meters per second, which, as we worked out before, was 24 miles an hour, give or take. So yeah, so there's two ways of working it out. One is obviously a lot easier than the other, but as it should, they both gave the same result. A little bit too accurate, to be honest. There were a lot of errors in some of my measurements. I think I got lucky and they all cancelled out. Right, so that's pretty much it for this video. I just want to say, maybe he was in the right, maybe I was. Certainly in a built-up area, always watch your speed, because you never know what's going to happen. And if you're crossing a road, always stop and look, rather than just cycling out into the middle of it. So anyway, hope you enjoyed it, and I will see you next time.